Thanks a lot for the kind invitation. I'm very happy to be back in this called Genosk seminar. It's been there have been wonderful talks, and um, so today Bernhard told me that I should give a colloquium style, very general, broad audience type talk about this specific topic on the application of geometric variational methods in scalar curvature. So you may, some of you may already have been quite familiar with the approach, but I'll start from the basic stuff nonetheless. Okay, so the one type of question in the differential geometry is to understand the so-called obstruction problem of curvature. So, the basic, the general theme is that you're given a curvature condition, and we ask which smooth manifolds admit Riemannian metric with this kind of condition, where specifically you can ask the manifold, you can require the manifold to be closed or complete generally. Okay, so such questions are, extremely classical, and there are results on sectional and Ricci curvature, very fruitful research in this area. A lot of them are already in the textbook. Classically, for instance, to study Ricci or sectional curvature, some classical approach include the variational methods, but specifically the second variation of the length function on geodesics, and another main theorem is the Buchner technique. Okay, so these approaches, people have been trying to extend these kind of approaches to the study of scalar curvature, and there are certainly challenges. And as we know, scalar curvature is a pretty weak local measurement of bending. Okay, so specifically for scalar curvature, we need to make sense of the appropriate curvature conditions to have any let's say any possible restriction on the global topology at all. So in this regard, there's a classical result by Carsten-Werner. So given any three manifold of dimension at least 3, then I'm sorry, n here is the dimension of this manifold. Then any function which is negative somewhere can be realized as a scalar curvature function of some Riemannian metric. Okay, so it doesn't quite make sense to talk about the obstruction problem, the topological obstruction problem for scalar curvature if your scalar curvature is not always positive. Okay, so then people then
one question, Chao. I have one question. Is M? Do you assume that M is compact here, or is this?
Oh yeah, closed. Let's say. Closed.
Okay, closed. And is it also true for non-compact M? If we look for complete metrics with this.
Let me see. So yeah, okay. So I don't think this Carsten-Werner theorem directly implies that, but I do think there's this construction by Lowkamp. I understand that's based on H principle. So I think you can do a local deformation to decrease scalar curvature as much as you want.
That's true. Yes.
Right. So it's still even for a complete metric. Yeah. So
that's the Hammock's paper, right? Hammock's.
Yeah. Right.
Yeah. Okay.
So that's a local construction. So even for complete metrics, it doesn't quite make sense to talk about the scalar curvature obstruction if you allow negative curvature there. Okay. So so then people look for obstructions for positive scalar curvature. Right? So I'm going to abbreviate in this talk PSC for positive scalar curvature, and the first such obstruction, I believe, was found by Schneeries in 1963. So the obstruction was coming from the so-called Schneeries formula and the Atiyah-Singer index theorem. So particularly, it applies to closed and spin manifolds of 4K dimensions, and if there's a positive scalar curvature metric, then this A hat genus. So this is a differential invariance of the manifold. So that has to vanish. So particularly, this rules out a lot of interesting previously unknown cases. For instance, K3 surfaces, right? So K3 do admit, let's say, scalar flat or even Ricci flat metrics, but its A hat genus is non-zero, and particularly it doesn't admit any metric with a positive scalar curvature. Okay, so this is a really exciting result, and then people look for some examples which are, and I would understand that's at the borderline of this kind of results. Okay, so one particularly, well, okay, so then we specifically in this talk focus on, one focus of this talk is this obstruction problem for positive scalar curvature, so which smooth and closed manifolds admit a positive scalar curvature Riemannian metric. Okay, so now a particularly interesting example to focus on is the so-called torus. So we take the very basic example, the Cartesian product of n copies of the S1 of the circle, and that's the n torus. So this example is, I would understand that's, at borderline of the Lichtenerius approach. So it's on one hand, obviously it means a flat metric, but on the other hand, its A hat genus is 0. So the original spinor argument does not quite work here. So it turns out that it's also related to the existence of positive scalar curvature metric, or non-existence of it. It's also related to some questions raised naturally in mathematical general relativity, and it's known as the Girard conjecture. So the conjecture states that for all n-dimensional torus, for n at least 2, or for all n at least 2, the n-dimensional torus does not admit any positive scalar curvature metric. Okay, so it's actually solved completely. So there are, and its solution motivates two main, I would say, techniques to study positive scalar curvature problems. And the first approach was done by Schoen-Yau, and that uses minimizing hypersurfaces. So particularly since it's a minimal surface proof, and classically it requires dimension to be at most 7 to guarantee regularity. And the second approach was discovered by Gromov and Lawson, and they used a very clever twisted spinor approach. So in this talk, I'm going to focus on the first approach, and I'm going to introduce you how we can use minimal surfaces and other geometric variational methods in the study of scalar curvature. Okay. So let me focus on the first Schoen-Yau approach using stable minimal hypersurfaces. So the basic observation by Schoen-Yau is, well, can be summarized in this very short sentence. Namely, if you have let's say a two-sided stable minimal embedding or even immersion, let's say into a ambient space, let's say, with positive scalar curvature, we assume the scalar curvature of the ambient space is positive, then the minimal hypersurface here, M, also admits a metric with positive scalar curvature. Okay, so you somehow, from a ambient space with positive scalar curvature, obtains a hypersurface inside, which also admits positive scalar curvature. So you can imagine that if one can repeat this argument, then we eventually go down. We can inductively descend the dimension from n+1 eventually to 2, right? But for surfaces, it's very easy to tell which one has positive scalar curvature and which does not. Okay, so to specifically introduce the technique, let's recall here that a submanifold is minimal if and only if its first variation of area is 0. So equivalently, it has 0 mean curvature. And here I assume that the surface is two-sided. So the two-sided stability is it means that the second variation of the area is non-negative, and it can be written in the following eigenvalue condition. So for every compactly supported function f, well, this quadratic form in f is non-negative, so it has a gradient term and some curvature term times f squared. Okay, so the crucial observation of Schoen-Yau is that one can actually use the traced Gauss equation to rewrite this curvature term into a form that relates the ambient scalar curvature and also the scalar curvature of the minimal submanifold, well, minimal hypersurface, I'm sorry. So, and particularly we're going to use this version of the second variation in the later discussion.
Okay. Chao, one question.
Yes.
You talk about two-sided minimal hypersurfaces. What about dropping this assumption?
Right. So if you drop this assumption, then well, we're dealing with a one-sided, let's say a one-sided hypersurface, generally speaking. In that case, okay. So it still makes sense to talk about stability, but the stability is not given in this simple form of eigenvalue condition. Okay. So,
okay.
So here, in order for this to make sense, I'm actually implicitly assuming that in the two-sided case, I'm assuming that the variation is given by f times the unit normal field. But now, if you do not have a unit normal vector field globally defined, then you can't really do that. Still, you can take the double cover, for instance. Then in the double cover, you can well, the one-sided stability tells you that in the double cover you still have this condition, but for functions f invariant under the that transformation essentially. So yeah, it's a less powerful condition. Okay. Right, but that's really a big problem for some further applications, I would say, because the next step, as we will see, will break down in the one-sided case. Though. Okay, so there are two ways to use this to use the Schoen-Yau observation. I would understand it as two interpretations of the inductive descent argument of Schoen-Yau. And the first one, which is I think the first really also in the canonical order, is the conformal interpretation. So let's remember that on a on any Riemannian manifold, we can consider the conformal Laplacian. So this is just the minus Laplacian plus a dimensional constant times a scalar curvature. Okay, and here the dimensional constant is something n-2 over 4 times n-1. So this operator naturally appears in conformal geometry, and particularly if we conformally deform the metric Riemannian metric by the specifically chosen power of the positive function u to 4 over n-1, then the new scalar curvature is related to the previous one by this simple formula. So the important part is the conformal Laplacian acting on the function. Okay. Now here n is the dimension of the Riemannian manifold. So particularly if we compare this this operator with the stability operator, so stability again gives us a eigenvalue condition. So positivity of this eigenvalue condition gives us the positivity of the associated elliptic operator. And here that operator is the sometimes called Jacobi operator. But specifically, if we look at the stability inequality and the condition that the scalar curvature of the ambient space is positive, then now let's go back real quick. So these two terms are positive, so I can just throw them away, right? So in this stability inequality, and then the eigenvalue condition implies that the first eigenvalue of what's remaining in the operator, so namely it's the minus Laplacian plus 1/2 times the scalar curvature of the minimal hypersurface is positive. Okay, now this operator is strictly large. Well, okay, strictly larger larger than the conformal Laplacian, simply because the dimensional constant Cn appeared in the conformal Laplacian strictly less than 1/2. Okay, so then from stability inequality and the condition that the ambient scalar curvature is positive, we deduce that the first eigenvalue of the conformal Laplacian is positive. So in this case, then we can just take the first eigenfunction of the conformal Laplacian and do this conformal deformation. And the upshot is that the G tilde metric will have pointwise positive scalar curvature. Okay, so the upshot here is that through this conformal interpretation, one concludes that any stable minimal hypersurface M is conformally equivalent to a positive scalar curvature Riemannian metric. Okay, so you do get a PSC Riemannian metric of one dimension lower through this conformal change.
So you also use that the first eigenfunctions for the first eigenvalue don't have zeros, right?
Oh yeah, here, right. So the first eigenfunction of this kind of Schrodinger operator is always positive or negative. Let's say positive in this case. Right.
It's quite amazing, actually. I mean, it's it's pretty nice that this is the case.
Yeah, right. Yeah.
Okay.
Everything patch up, very nicely in this. Okay. Okay, so this is a very nice and very convenient way to do this to make sense to make use of the stability inequality. On the other hand, it does have some drawback compared to the second interpretation, which I call it word product interpretation. I think Misha Gormov usually calls it toric stability or torus stability. It's basically they basically mean the same thing. So the observation is the following. So now let's take the first eigenfunction of the stability operator. So the stability operator is positive. Therefore, if we take the first eigenfunction, the eigenvalue is also positive. Then what we can do is that we can consider a word product metric. So we take the minimal hypersurface that's of dimension, let's say codimension 1, and we take its product, Cartesian product with S1 factor. But on this product manifold, I take the induced metric on M with the U squared times dt squared on S1. Okay, so U is the first eigenfunction. All right, a simple computation shows that if we compute the scalar curvature of this word product, then I mean this is equality for for every positive function U. So then one gets minus 2 times U inverse times Laplacian U minus 1/2 the scalar curvature M times U. Okay, so particularly this is this factor equals, since we're taking the first eigenfunction, equals the first eigenvalue plus Rx plus A squared. Okay, so that's precisely from the operator. And since we assume the stability in the first eigenvalue of the stability operator is non-negative, then we deduce that the scalar curvature of this word product is larger than or equal to Rx plus A squared. Okay, so through this word product technique, we not only gain some new manifold with positive scalar curvature. Well, the additional advantage we get is that the scalar curvature lower bound is preserved in this process, right? So starting from the original Rx, we get something with even slightly larger scalar curvature. Okay. Okay, so this is very useful, and in either way, so you can do the conformal change where you can just repeatedly do the word product. So let me maybe show you how to do the word product in a repeated manner. So basically, what we do is that it's called inductive minimal slicing by Schoen-Yau. So essentially, what we can do is the following. So let's say we start with the n+1 dimensional manifold, and we take somehow, say we can find a stable minimal hypersurface with first eigenfunction of the stability operator UN. Then we first cook up the word product metric on M cross S1, and then we minimize again in the word product. Okay, so then we just repeat this process. So inductively, suppose we have already found a sequence of minimal hypersurfaces, each of codimension 1, and then what we do next is that we take the kth minimal hypersurface of this is of dimension k. So let me emphasize here. So this is dimension k. Okay, then we inside MK cross all the remaining S1 factors coming from the previous slicings, we find a minimal hypersurface well in this word product, but invariant for the torus factor. Okay, so in other words, we minimize volume with respect to the word product metric. The GK is the induced metric on MK, and then you warp it with all the previous Jacobi eigenfunctions. So these are all the previous Jacobi eigenfunctions as warping factors. Okay. Okay, so one can do that, or equivalently, if you do not want to talk about this S1 invariance of minimizer, an equivalent way to do that is on the inside MK. So inside MK, you just find a minimizer of the weighted volume function of just weighted by the previous Jacobi eigenfunctions. That's also fine, right? So you can minimize for this weighted volume. Nonetheless, then once you can do that, you get the next object in the minimal slicing, and so the advantage, as we discussed, is that the scalar curvature lower bound is preserved in the integral sense. So it's preserved in the in each of the word product, and that's an eigenvalue condition again on each minimal slicing. Okay, so that eigenvalue condition guarantees the following important results. So if you can slice down all the way to dimension 2, then this two-dimensional surface, this eigenvalue condition, is what we call scalar curvature positive in the integral sense. So this M2, the two-dimensional surface, behaves like a two-dimensional surface with scalar curvature bounded below by 1, the same scalar curvature lower bounds. Okay, so although it's not point-wise, the integral sense is enough to guarantee this similar geometric behavior. So particularly, those are only spheres with the so particularly each connected component of M2 has to be a sphere. So that's Gauss-Bonnet theorem. So positive curvature surfaces are spheres. And also we have the Bonnet-Meyer theorem. They all satisfy a suitable diameter upper bound. So it's 2 pi is not the optimal upper bound, but still it's close to that, and it's useful in most scenarios. And if you further can slice down all the way to 1 dimension, so then you really get just the circle, and then the circle should have an arc length upper bounded, depending on the curvature lower bound. Okay, so this is the second what we call the word product interpretation, or Gromov would call it the toric symmetrization technique. Okay, so it's a sort of equivalent. It should be equivalent to the conformal descent interpretation, but in reality, I think the word product is more useful. Any questions so far? Okay, so let's continue. Now, let me give you some remarks. So previously, we see that if we are able to find such a minimal slicing, or equivalently, if we can find a conformal descent, then we're able to say a lot of things on the final object. So when we go down all the way to dimension 2, okay. So so the existence of such a minimal slicing is usually guaranteed by topological assumptions. So if you have sufficiently many topology on the ambient space, then you can just minimize again in homology classes. And particularly this works if the ambient space you start working with is a torus. Okay, so there are a lot of homology.
Chao, I do have a question, respectively a remark. Do I understand correctly? So in the original Schoen-Yau argument, we have this descent method, and each manifold 1 dimension less has a positive scalar curvature metric. But somehow when we do this inductively, we forget the reason why it has a positive scalar curvature metric, while in this symmetrization process, we keep this information all over the induction. Is this the correct point of view, or?
Yeah, well, okay, so yeah, it's right. So I think this is of course one correct way of interpretation, but in my view, the more important property is the preservation of the same scalar curvature lower bound. That's okay. I mean that's not something that the conformal descent can.
Right. Okay.
Of course, if you just care about the sign of scalar curvature positivity, then fine, conformal descent does that. But in a lot of applications, you do need a quantitative geometric geometric estimates. Like we do want to quantitatively control the diameter upper bound, for instance. And in that case, I think the symmetrization or the word product is the only approach that does that.
Yeah, thank you.
Okay, so let me briefly discuss a little bit on what I believe Tian-Yao will focus on in the next talk. So similar ideas have been extended to other scenarios and important applications. For instance, scalar curvature has a physics meaning in the mathematical general relativity, and that's non-negativity of scalar curvature is sort of meaning that for time symmetric initial data sets, the energy density is non-negative because it's a very natural condition. But for instance, when we look at not necessarily time symmetric situations, then we are dealing with initial data sets in general relativity with the so-called dominant energy condition. So that's a more general condition on non-negative scalar curvature. Okay, so there. People also consider, I think it's also motivated partly by Schoen and Yau, so to study the topology of such of these more general initial data sets when one study mods, so they are marginally outer trap surfaces, so in place of minimal surfaces, and then there are also applications of the stability inequality in there. Okay, so that's an important extension. Okay, so to summarize what we have discussed so far, it's fair to say that stable minimal surfaces are our friends in positive scalar curvature. Okay, so in a lot of cases, we can find one. What have we done, essentially? Now, the drawback is that the stable minimal surfaces are not easy to find. So if you think about how do you find a stable minimal surface in the first place? Well, the way I can usually imagine is that they arise as minimal, area minimizing hypersurfaces. Okay, so if you can somehow minimize area in homology class, of course that's stable. Or you can take limits of such surfaces and assuming such limit exists, then the limit is always also stable. But beyond these scenarios, it's very difficult in general to find, let's say, stable minimal surfaces. Okay, so. But scalar curvature condition itself is not strong enough to guarantee any sufficient topology to the existence of stable minimal hypersurfaces or area minimizing surfaces. And one observation here is that the inductive slicing argument that we just described only uses the second variation property. Okay, so in the process, we didn't really strongly use the fact that the mean curvature vanishes for the first variation 0. So the bright idea is extremely clever idea, I think, initiated by Gormov is that one should try to construct two-sided hypersurfaces with a similarly good eigenvalue property coming from a suitable second variation, but not necessarily not necessarily stationary for the area function. Okay, so that's the important idea that's that has been greatly developed in the past few years, and so these objects are called Gormov's mu bubbles. So the use of these bubbles dates back to 1996, and so the hope is to try to, as described before, to try to construct similar nice geometric objects in the row of stable minimal hypersurfaces, but are more flexible and the existence is more it's easier to guarantee. So let me discuss the basic setup of this construction. So the basic setup is the following. So I have a manifold with boundary, but the boundary, let's say I have, the boundary could be quite complicated. Also some topology inside. Okay, so this is our X, but then I should be able to group the boundary components into two disjoint families, and one, let's call it boundary plus, and the other. So these two together, I'm going to call it boundary minus. Sorry, what's going on? Okay, so then the scalar curvature, let's assume it's uniformly bounded below by some positive constant, say 3. Okay, the 3 number doesn't matter much here. Okay. Now, what we do is that we consider the following variational problem. So among all relative open sets omega, containing one boundary, the boundary plus and is disjoint from boundary minus, we consider the following functional, namely we consider the area of the reduced boundary and minus the integral of a function in the open set. Okay, so on picture it would be something like this. So we consider such a, let's say this region would be our omega, and so then with this notation here, these guys are the reduced boundary omega. So we're minimizing their area, but also minus the integral of a certain function in omega. So and notice that if h, the little h function is 0, we're just minimizing the area of the boundary. Okay, so this in other context is called the prescribed mean curvature functional. So the reason, let me briefly mention, is that the stationarity. So the first variation tells us that the mean curvature on the reduced boundary it equals pointwise to this little h function. Okay, so you prescribe the mean curvature to be little h. Now, what's more important is the second variation. So let's call the reduced boundary M. Then M satisfies a eigenvalue condition, which is quite similar to the stability of minimal hypersurfaces, but with this additional terms depending on h. Now, the observation is that if we can choose h in a clever way, okay, for instance, h is larger than the mean curvature of the barrier del plus and del minus, particularly if h tends to plus or minus infinity appropriately on this two boundary, then the minimizer always exists in the middle. Okay, so notice that in this argument, there's no topological assumption needed at all. So you can somehow always find the minimizing surface. Okay, so then let's try to make the stability useful like before. So on the right-hand side, we have exactly the same eigenvalue, expression, quadratic expression in F. On the right-hand side, I have some terms depending on h. So the upshot is that if we can squeeze a little bit, let's say squeeze epsilon from the positivity of a scalar curvature term, ambient scalar curvature term, and move to the right-hand side, and guarantee that and make choose an h function such that this inequality is true, the expression on the right-hand side is positive pointwise, then the conclusion we get is that the first eigenvalue of this important operator on the hypersurface on this mu bubble is larger than or equal to the original scalar curvature, but you just lose a tiny bit, arbitrarily small bit. Okay, so the choice of such a function h should satisfy both the condition that h tends to, let's say, plus or minus infinity and this inequality. So there are, for instance, such choices like h depending on the distance to one of the boundary components. So as a summary, as long as your two boundary components del plus and del minus are sufficiently far apart, say they are bigger than some universal constant dividing by your scalar curvature lower bound, then one can make all this happen. Okay, so it's a very flexible construction. Okay, and moreover, this construction respects inductive descent. So namely, if we started with not pointwise positive scalar curvature condition, let's say, instead of assuming, so this is to say it also works instead of assuming well, Rx is pointwise larger than 3. This is our assumption to start. But if we instead assume that its scalar curvature is positive in the integral sense, okay, so let's say this is one condition that's inherited from the inductive descent argument, right? So let's say lambda1 of minus Laplacian plus 1/2 R is larger than some positive constant, then you can also do this. Okay, so warp it with the circle factor and repeat the process, minimization process. Okay, so each of the steps carries through. All right, so then one can try to just use this these mu bubbles in the place of stable minimal hypersurfaces in the inductive descent argument. And that's proven very useful, and particularly it's well suited because of these distance conditions, well suited to study microscopic geometry of scalar curvature. Okay, so that's where this mu bubble has become very powerful at. Let me quickly tell you what it remind you of the definition of the so-called Urisan width. So we say a Riemannian manifold has Urisan k width bounded above by lambda if there exists a k-dimensional simplex and a continuous map from your manifold to k such that the pre-image O has diameter bounded by lambda, for instance. So this is saying that in the microscopic way, your manifold has looks like a k-dimensional simplex. So it's something like you could have a topology somewhere here and there. But say this picture, you want to say it looks like a one-dimensional simplex. How? Well, imagine that you can, you can draw this kind of pictures, and sort of the entire picture collapse to the one skeleton without losing too much information on distance. Okay, so that's what it means to be to have Urisan k width bounded by lambda. All right, and the big conjecture in this direction by Gromov is that if there is a scalar curvature lower bound on a closed manifold, then the n-2 dimensional Urisan width is bounded by some dimensional constant. Well, actually, in this conjecture, we do not even need to assume X is compact or closed. Okay, so it also makes sense for manifolds boundary and also for complete manifolds. So one can also study similar properties by replacing the diameter in the definition by other geometric quantities. For instance, you can try to estimate the area of each pre-image or the volume of each pre-image, etc. Okay, so they all make sense. So microscopic geometry is a sort of a geometry that that measures the metric properties, or metric properties in a very coarse sense. So it's a very nice property to study. And the applications of the mu bubbles are very interesting in studying this kind of microscopic geometry. So for instance, there are, and let me just list a few names. It's by no means an exhaustive list. So there have been important bandwidth estimates under scalar curvature lower bounds by Gromov and Zetlers-Cheney and Tianzhu and etc. So there are lots of interesting results in this direction. And also directly related to microscopic geometry, there have been interesting development when the dimension is 3. So the Gromov conjecture for 3 manifolds has been completely resolved. So all 3 manifolds with a scalar curvature larger than 1, or even in a weak spectral sense. When I say this, I mean I'm going to replace the pointwise condition by the lambda 1 condition. Okay. So this is what I mean by the weak spectral sense. Okay, so then we know that these manifolds are small in many senses. Okay, so first of all, the classical distance sense, namely, if X is simply connected, then it has bounded Urisan 1 width. That's done by Gromov-Lawson. And also, even if it's not simply connected, the statement is also true. That's a new result by Lyubomovich and Maximov. And also, it's small in it's one-dimensional or small in the area sense. So previously, I said you can talk about area of the pre-image. So in this case, what Otis Chodosh and I did, well, implicitly in our work is that for 3 manifolds with this condition, this X has evenly spaced separating surfaces. So these are 2-dimensional surfaces with a uniformly bounded area. Okay, so each of the small surfaces is small in area. And also, the volume growth of such manifolds could not be so large. So particularly if you assume Ricci is non-negative and you assume X is complete, then such a manifold X can only has linear volume growth. Okay, so it's really one-dimensional in the volume sense. In other words, so this was first done by Montino and Wang, and with Otis and Otis Chodosh and Doug Stryker, we gave a different proof using mu bubbles, and this mu bubble proof was recently, I think, also extended a little bit to find the optimal volume growth rate by Wei Xu and Zhang. So the volume also gives a one-dimensionality. So with all these tools in mind, for instance, I think an interesting development in this is in Mille bubbles is that the resolution of the so-called aspherical conjecture in low dimensions. So it was done independently by Chao Li and also by Gormov a few years ago. So a closed aspherical manifold of dimension at most 5 does not admit any Riemannian metric of positive scalar curvature. Okay, so this uses relies extremely on the flexibility of Mille bubbles. Okay, so one difficulty of this theorem is precisely that you cannot expect to find stable minimal hypersurfaces in general manifolds. But also it has its drawback, maybe. So compared to the classical descent argument, the Mille bubble is flexible to detect, let's say, large portions with portions of manifolds with long distance. But this property is hard to guarantee in the inductive descent argument. So, in other words, the Urisohn width does not, obviously also decrease in this inductive descent argument. Okay, so that's what makes the extension of this kind of arguments in higher dimensions very difficult. Okay, so this is a difficult problem. We've made some progress, but since it's too difficult, what we do in math is that let's try to work on some other related, but maybe more hopeful problems. And one such hopeful problem was the going back to my title, so to consider other similar or interesting curvature conditions. So for instance, one such curvature condition was studied by defined and studied by Brandel, Hirsch, and John in a beautiful paper. So they proposed the notion of CK curvature. So K should be between 1 and the dimension of the manifold -1. Okay, so these CK curvatures are interpolations between the Ricci and scalar curvature. So particularly, they depend on the K-plane, K-dimensional plane on a tangent space, in the tangent space. And particularly, they are defined to be the sum of all sectional curvatures in directions that contain at least one of the E1 to EK. Okay, so this is the formal definition. So some special cases, C1 is just the Ricci curvature, and C2 is called a bi-Ricci curvature. So I believe people have previously already studied bi-Ricci curvature. And Cn-1 is our scalar curvature. Okay. Now, the CK curvature also depicts some interesting properties under the inductive minimal slicing procedure. So particularly in their paper, Brandel, Hirsch, and John proved that take any closed manifold of m dimensions, then take the Cartesian product of that with the m-dimensional torus. So then this guy does not admit a metric of positive Cm curvature. Okay, so for n less than or equal to 7, and m is between n-1 and n-1. Okay, okay, so that's already very interesting. And what's more interesting is that well, actually, Kai. Oh, sorry, I should have used his last name. So it's Kai Xu. Okay, so he constructed counterexamples explicitly when the dimension is at least 8. Okay, so there are some interesting phenomena in this inductive minimal slicing computations for this more general curvatures, and that only holds in low dimensions. So on the other hand, the initial step of descent, so the descent from bi-Ricci positive to Ricci positive unstable minimal surfaces always hold in all dimensions. Well, now of course it's by positivity I mean positivity in the eigenvalue sense, so in spectral sense. So that's already something pretty interesting. So the bi-Ricci to Ricci descent carries a lot of useful information, as we will see briefly. So to have let us try to think about the standard picture of, or standard examples of Cm positive manifolds. So when m equals 1, again, Cm is the Ricci curvature. So Ricci positive means that, well, you're your fundamental group is finite. So one's basic example is the sphere. Okay, and when M is 2, the basic example is a sphere crossed with Cartesian product with R. So you're allowed to split one line essentially. And generally for CM curvature, it's well, I think one should view the CM positive manifolds as some compact portion, but you're allowed to split at most -1 directions. So one could try to think about this extend Courant's conjecture on the Urizen width to this more general notion of curvatures. For instance, one could hope to say that CM curvature larger than 1 implies that the Urizen M-1 width is bounded by some uniform constant. Okay, so it looks like at most an M-1 dimensional manifold in the microscopic sense, as these examples illustrate. Now, note that this is obviously generally false for large M by again, this is a Kai-Shu's counterexamples, but still that's an interesting question in low dimensions even. Okay, so it's far from being well understood. And what's more interesting is that, well, it's already known to hold for some special cases, special and simple cases, and Kai-Shu proved that it's true for M at most 5 and M equals 2. So this means that in these dimensions, bi-Ricci positive larger than 1, let's say, implies that the Urizen 1 width is bounded. So Urizen. There's a 1 width. It's uniformly bounded by some constant, depending only on dimension. Okay, and recently we've been very lucky to discover actually when n equals 4, so 1 dimension lower, and m equals 2, still in the bi-Ricci case, the microscopic statement is also true in the volume sense. So in other words, if you are a 4 manifold with bi-Ricci positive. So let me maybe write a few more words on exactly what I mean by this. So M4, G has bi-Ricci is larger than 1, then there exists, evenly spaced separating hypersurfaces. So these are 3-dimensional manifolds whose volume are uniformly bounded by some dimensional constant. Okay. So for 4 manifolds with bi-Ricci larger than 1, you can try to exhaust that by regions whose boundaries are having small volume. Okay, so this is actually a crucial step in our recent solution to the stable Bernstein problem for minimal hypersurfaces in R5. Okay, so I think the study of these kind of more general versions of the CK curvature problem is interesting, and I think they should also lead to other fruitful development in the in related areas. Okay, so maybe I'll stop here, and thanks a lot for the attention.